All right, let's jump right in. In today's explainer, we're diving into one of the most fascinating, game-changing shifts happening in AI right now. We're looking at the evolution of audio AI. And look, we aren't just talking about a machine figuring out the words we're saying. We are talking about a massive leap from basic audio transcription to complex, deep audio understanding and reasoning. It's a full-blown journey from just hearing words to actually understanding the entire acoustic environment. So think back to late 2022, a model called Whisper drops, and it effectively solves speech recognition. Boom! Trained on 680,000 hours of weekly supervised multilingual speech, it instantly became the gold standard. But, well, here's the catch with that. Because of Whisper, basic speech to text is now basically just OCR for audio. It's a total commodity. Now, don't get me wrong, recognizing words is incredibly useful, but recognition is definitely not reasoning. And this hits the nail on the head regarding exactly where that text-only approach hits a massive brick wall. Imagine you ask your AI, hey, what's the mood of this song? Or who's speaking right now, Alice or Bob? Or even, at what exact second does the explosion happen? If your AI is only looking at a text transcript, it's completely blind. Actually, scratch that, it's completely deaf to those answers. The mood is in the sound, not the text. A transcript strips away the emotion, it loses the speaker identity, and it totally ignores the environmental context. So how do we fix it? Well, here is our roadmap for this explainer. We're going to quickly cover 1. Transcription limits, 2. Feeding audio to AI, 3. Cascaded versus end-to-end, 4. Bridging with Q-formers, 5. The audio LLM evolution, and finally 6. The 2026 production recipe. First step, Section 1. Transcription limits beyond audio OCR. There's a quote from the source material that perfectly captures this whole problem. It says, if the model cannot reason over what it heard, timing, speakers, emotion, music structure, transcription alone cannot drive product features. The absolutely crucial takeaway here is that true product value in the next wave of AI comes from reasoning about the entire acoustic space. If you're trying to spot a deepfake or analyze a really heated customer service call, words alone just aren't going to cut it. Moving into Section 2, Feeding Audio to AI, the Technical Stack. Okay, so if plain text isn't enough, how on earth do we actually feed a raw, messy audio waveform into an artificial brain? Well, every audio encoder out there starts with the exact same input feature, a log-Mel spectrogram. And here's the literal recipe for it. First, you resample the audio to 16 kilohertz. Second, you slice it up using a short-time Fourier transform with 25 millisecond windows and a 10 millisecond hop. Third, you grab the magnitude of that FFT result. Fourth, and this is super important because it maps to how human ears actually hear, you apply 80 Mel filters, log spaced from 0 to 8,000 hertz. Finally, log compress it for dynamic range. And what do you get? A beautiful 2D array of time and frequency that the AI can actually look at. All right, so you've got your spectrogram, now you gotta encode it. Whisper has a ridiculously good encoder for linguistic signals, the spoken words. But it's kind of tone deaf when it comes to music and environmental sounds. So the big brain move here, which you see in cutting-edge models like Audio Flamingo 3, is using an AF Whisper hybrid encoder. You literally take the Whisper features for the words, and you bolt them together with features from an encoder called Beats. Beats was trained on a massive dataset of environmental audio, so it completely nails the music and the acoustic space. Stick them together, and you've got the best of both worlds. Which brings us to Section 3, Cascaded versus end-to-end, the architecture battle. When you're building one of these audio pipelines, you're basically standing at a crossroads. You've got two choices, cascaded or end-to-end. In a cascaded setup, Whisper transcribes the audio into text, and then a standard large language model reasons over that text. It's great if you just want to summarize a podcast, but you instantly lose all that rich acoustic information we talked about. End-to-end, though, that skips transcription entirely. The audio features feed directly into the LLM. This preserves the whole acoustic signal. Suddenly, the AI can natively understand a speaker's emotion, untangle overlapping voices, and even catch those tiny acoustic glitches in deepfakes. But hold on, how do you actually wire a raw audio encoder into an LLM that only thinks in text tokens? That takes us to Section 4, Bridging with Q-formers, the universal translator. Right here is where the magic happens, the audio Q-former. Think of this little component as the ultimate universal translator. It acts as a cross-attention bottleneck. You take your massive flood of audio encoder frames and you run them through a fixed number of learnable queries, usually around 32 or 64. These queries filter through all those audio frames and crunch them down into bite-sized audio tokens that the LLM can digest right alongside normal text tokens. It is the absolute vital bridge that makes end-to-end training a reality. Next up, Section 5, Audio LLM evolution, the arc to reasoning. Now that we've got the architecture down, let's look at the timeline because honestly, the pace of this is just staggering. We started with Whisper doing basic speech recognition in December 2022. Fast forward to 2023, we saw early audio LLMs like Salmon and LTU that started snapping Q-formers onto language models to unlock actual reasoning. By late 2023, we got Qwen Audio, which fine-tuned everything for multi-turn dialogue. And that rockets us to the current open-source state-of-the-art, Audio Flamingo 3. Released in July 2025, it's built on a massive 8 billion parameter LLM backbone and trained on over 1 million audio-text instruction pairs. Okay, but the real question, how good are these models getting in the real world? Let's talk MMU benchmark. That stands for Massive Multimodal Audio Understanding, and it's a brutal test of 10,000 complex audio questions. Salmon scored a 0.55. Audio Flamingo 3 jumped all the way to 0.72. Meanwhile, the absolute bleeding edge, closed, proprietary frontier models are hovering around 0.78. This is huge. It shows just how incredibly fast the open source community is closing the gap. You want to know the secret weapon behind that huge jump? It literally comes down to a single number, 3 to 5. That is the exact point boost that Audio Flamingo 3 gets on complex reasoning tasks, just by using something called on-demand thinking tokens. Check this out. Before giving an answer, the model is trained to spit out tokens that say, hold on, let me identify the instruments first, or let me listen to the background noise. By forcing the AI to explicitly reason about the sound before answering, its accuracy spikes by up to 5 points. It's brilliant. Finally, Section 6, the 2026 production recipe, what to build with. Let's bring this whole thing together. If you're building an AI product right now, here is your cheat sheet. If your only goal is basic transcription, you literally just need a text log of some clear speech, stick to a cascaded pipeline. It's cheaper, simpler, and gets the job done. But if your use case touches music, inferring human emotion, dealing with multiple people talking over each other, or complex environmental reasoning, you have to go end-to-end with a model like Audio Flamingo 3 or Qwen Audio. It preserves the acoustics and unlocks that deep reasoning you need. To wrap up this explainer, I want to leave you with a thought. If injecting a chain of thoughts, making the AI stop and internally listen to the instruments before answering, lifts accuracy by 3 to 5 points, what other audio tasks absolutely demand thinking first? Imagine an AI diagnosing failing machinery just by listening to the motor hum, or an emergency AI triaging a chaotic, noisy 911 call in real time. The possibilities of multimodal reasoning, we are just getting started.